In 1896, Dutch scientist Peter Zeeman was experimenting with an optical diffraction grating to see how magnetic fields might affect it. What he observed was the splitting of spectral lines now referred to as the Zeeman effect. This discovery led to the 1902 Nobel Prize for Dutch physicist Zeeman and Hendrik Lorentz. In 1897, Irish physicist Thomas Preston found very startling results where many more variations of the effect were found, and there was no good explanation for this. In 1925, two graduate students at Leiden hypothesized that the mysterious observations were caused by the concept of spinning electrons. The term spin originated from the early idea that electrons were physically rotating around an axis, like how a planet spins. The true nature of spin is a much more abstract quantum mechanical property with no classical analogy to actual rotation, but the name spin stuck and is used to refer to this property to this day. That same year, Wolfgang Pauli proposed the exclusion principle by stating that no two electrons in an atom can have the same set of properties defined as quantum numbers. This added a fourth quantum number for spin to describe the state of an electron in an atom. All particles with half-integer spins called fermions are subject to the Pauli principle. Electrons in an atom, protons in a nucleus, and quarks in a hadron are all fermions. Because quarks have yet another quantum number, called color, only similar quarks with the same spin and color are forbidden to be in the same state. Particles with an integer spin are called bosons and are not subject to the Pauli exclusion principle. This has dramatic consequences for the structures that they can form. Bosons can occupy any state free of the Pauli exclusion and are only limited by their interactions they encounter. As a result, they can only form fluid or soup-like structures. Fermions, on the other hand, must follow the Pauli exclusion rules and can only fill states alone or with unlike equals, forming more orderly structures. This is why atomic electrons organize themselves into shells. These arrangements form the basis for the periodic table, which groups atomic elements according to their structure or their electrons and chemical properties. A similar spin-based ordering system determines the arrangement of protons and neutrons in the atomic nuclei. This leads to a huge abundance of nuclei such as helium-4, oxygen-16, and calcium-40 found in nature. Spin gives rise to magnetism with countless applications. Giant magnetoresistance can create powerful magnetic field sensors, such as those in computer disk drives. MRI scans, or magnetic resonance imaging, uses the spins of protons to probe our bodies and is an everyday medical diagnostic tool. Special electron spin states are also harnessed to develop precise atomic clocks with an accuracy less than 1 second over the age of our universe. Controlling spins in semiconductor materials can be used for quantum computing, and entangling spins can be used for quantum communications. Spin led to structure and order in the elements and atomic nuclei. And how about the proton, the nucleus of the hydrogen atom, the dominant source of mass in the visible universe? Protons, neutrons, and other hadrons are particles composed of quarks and gluons. Hadrons with a spin of 1/2 are referred to as baryons. A major realization in the 1960s was that their mass ordering is determined by symmetries associated with the flavors and spins of the quarks, which can be organized into the baryon octet. This classification led to the 1969 Nobel Prize for American physicist Murray Gell-Mann. The proton is an absolutely unique quantum system in which quarks and gluons move near or at the speed of light. In the tiny quantum world of the proton, there exists a sea of particles that continually pop in and out of existence. As a result, the proton changes depending on how it's observed, manifesting itself in very different ways. The proton is a fermion and has a spin of 1/2. This spin can have two states, spin up or spin down, and the spin's orientation in 3D space can change, and is also in a state of superposition. Inside the proton, we see that it's made up of even smaller particles, valence quarks, which are also fermions with a spin of 1/2. and gluons, which are bosons with a spin of 1. In addition, there is a sea of quark and antiquark pairs constantly emerging and annihilating each other. These also have 1/2 spin for the quarks and a full spin for the gluon binding them. The up and down quarks are distinguished by enclosing them in up and down pointing triangles. These are all artificial labels that we have assigned them. The universe is aware of the quantum numbers that the point-like quarks and gluons carry. At such tiny scales, quantum effects come into play. Light-speed quarks and gluons can appear and disappear. Quark spins will flip upon the exchange of gluons, and orbits are not fixed due to strong spin-spin and spin-orbit interactions. When aligning the proton's spin to the proton's motion, we observe an increased probability for the spin of up quarks and gluons to align with this direction. For the down quarks, the opposite is observed. The up and down quarks will show roughly equal orbital motion, but travel in opposite directions. What we are trying to understand is how much these changes are and why. Powerful accelerators at Jefferson Lab and Brookhaven National Laboratory manipulate the spin of particles to help scientists study the deepest structure of visible matter. These are billion-dollar scale, one-of-a-kind research facilities funded by taxpayers that enable transformational science, develop cutting-edge new technology, while training the next generation of high-technology workers. Jefferson Lab has pioneered the realization and operation of large-scale superconducting radio frequency accelerator technology to produce intense, polarized electron beams. The SRF technology is now widely used in large-scale facilities worldwide. Brookhaven National Laboratory has developed the world's first and only polarized proton-proton collider using novel magnet technology. This will be essential to deliver the polarized ion beams at the future electron-ion collider. After 100 years of study, the roles of spin and charge have been well established in quantum mechanics. This century-long journey has brought us to a new frontier inside the proton, where spin adds a powerful window into the color force that binds quarks and gluons. Experiments with spin-polarized instruments started 50 years ago and matured in the 1990s and 2000s, with world-class unique capabilities developed at both Jefferson Lab and Brookhaven National Laboratory. Manipulating spin is a young quantum technology that we expect to flower in the 21st century. Both black holes and protons are unique examples of relativistic systems in nature, yet on vastly different scales. A black hole is the ultimate example of a massive classical relativistic object, with its properties arising from general relativity. But a proton is the ultimate example of a tiny quantum relativistic object, with its properties emerging from the high-speed relativistic motion of its internal components and their interactions. Most significantly, unlike the black hole, we can study the proton in the laboratory using powerful electron accelerators at Jefferson Lab and with the future electron-ion collider at the Brookhaven National Laboratory. Spin plays a central role for these accelerators to help understand how up and down quarks, the quark sea and gluon oceans, their spin, their color, work together to lead to the structure of matter at its deepest quantum level. We will be able to finally understand how the proton's constituents create spin. Experiments with polarized ion beams can point to the existence of exotic gluon and nuclei. Surprising discoveries are bound to emerge, leading to the development of new technologies right out of science fiction.